Imagine a 118-degree heat wave in Phoenix, and the power grid completely collapses. Within 4 hours, your home hits 95 degrees. Within 12, it crosses 104. Doctors don't call this uncomfortable. They call it unsurvivable. Engineers classify your modern home as a design failure. Your AC isn't a cooling system, it's a dependency. One grid blackout on the hottest day of the year, and the building you live in turns against you. But 1,000 years ago, builders in China solved this completely. Without a compressor, a power line, or a single moving part. They didn't just build homes, they engineered systems that mastered their environment using a toolkit of thermodynamic strategies. Today, we tear that machine apart, component by component, to see how they did it and why we abandoned the one technology that could actually save us. Before we get into the ancient solution, we need to be precise about the modern failure. Standard American residential construction uses wood framing and drywall, 1/2 inch thick, near zero thermal mass. Heat moves through it in minutes. When outdoor temperatures climb past 100 degrees, the building envelope offers no meaningful resistance. It is a shell, not a system. A modern home without air conditioning in a 100-degree environment becomes physiologically dangerous within hours. There is no buffer built into the structure. The walls do not absorb the heat or delay it. They pass it straight through. And the machine we built to compensate for that failure is enormous. Air conditioning now consumes 10% of all global electricity. In Texas, on peak summer days, cooling loads represent 50% of total grid demand. The grid strains hardest exactly when it is needed most, and when it fails, the homes it was propping up have nothing to fall back on. A multi-day blackout during a major heat wave in Phoenix is projected to cause heat-related mortality to rise by 700%. Approximately 13,000 deaths, more than 800,000 residents requiring emergency medical attention. A city with roughly 3,000 emergency room beds. That is not a weather problem, that is an architecture problem. Every engineering problem has a prior solution. Before mechanical refrigeration existed, people in hot climates survived and thrived. The question is not whether passive cooling works. The question is how precisely it was engineered and why we walked away from it. The answer was built into the walls, literally. Traditional Chinese courtyard architecture is a blueprint for survival. In the arid north, builders perfected the Siheyuan to maximize thermal mass and capture sunlight. In the humid subtropical south, they evolved the Tianjing, or Skywell, to prioritize ventilation and moisture control. While the specific architecture changed to suit the climate, the underlying thermodynamic principles, thermal buffering, the stack effect, and evaporative cooling remained the same. It was a regional science of survival. These buildings utilized a toolkit of 5 primary engineering strategies. While not every house contained all 5, they were the modular building blocks used across different climates to master the environment. Remove these strategies, and the building becomes a furnace. Keep them, and the structure maintains comfort using nothing but the sun. This system was not primitive. It was complete. The builders understood thermal mass, fluid dynamics, latent heat transfer, and solar geometry without the vocabulary we use today. And in some cases, modern computational simulations are only now catching up to what they built by hand. The first component does the heaviest lifting. In the arid northern Siheyuan, exterior walls were built from thick rammed earth, hangtu, or heavy brick to block the intense sun. In the humid southern Tianjing homes, builders utilized dense brick and timber. While the materials changed by region, they were similarly engineered for maximum density and climate-appropriate thermal buffering. Modern insulation slows heat transfer by trapping air pockets. It resists conduction. Rammed earth does something different. It stores heat. Its volumetric heat capacity exceeds 1,600 kilojoules per cubic meter. That density creates thermal lag, the time delay required for heat to conduct through a solid material from one face to the other. Here is what that means practically. Solar radiation strikes the exterior wall face at noon. The wall absorbs it. But for a wall 450 millimeters thick, the thermal lag runs 8 to 10 hours. That heat does not reach the interior face until after 10 p.m. When the sun has set, outdoor temperatures have dropped and the stored heat radiates outward into the cooling night air rather than inward into the living space. The wall does not block the heat. It delays it, absorbs it during the day, releases it at night when it causes no harm. Compare that to modern drywall. Half an inch, thermal lag measured in minutes. The air conditioner compensates for what the wall cannot do, and you pay for that compensation every month for the life of the building. The rammed earth wall is a thermal battery. The drywall is an energy sieve. But storing heat is only the first problem. How do you flush hot air out of the centre of the building without a fan? In the humid southern regions, builders designed the Tianjin or Skywell. This central courtyard acts as a pressure difference generator. Direct sunlight strikes the paved floor, heating the air, which rises via the stack effect. This creates a vacuum, drawing in cooler air from shaded side alleys, called cold lanes. Modern computational fluid dynamics simulations confirm that the orientation of these lanes acts as a passive ventilation engine. In a well-engineered home, this can reduce the annual cooling load by the equivalent of over 28,000 kilowatt-hours, a massive testament to the efficiency of passive design. But moving air alone does not lower temperature. To do that, you need a phase change. You need to turn that airstream into an active coolant. Stone water jars, cisterns, decorative ponds, localized plantings, placed with deliberate precision directly in the path of the incoming airstream at the base of the skywell. The physics is latent heat of vaporization. When water evaporates, it absorbs thermal energy from the surrounding air to break its intermolecular bonds, converting sensible heat into latent heat locked inside water vapor. The air loses that energy. It cools. Water has an exceptionally high latent heat of vaporization. Even modest evaporation rates produce substantial cooling, and because the skywell's air pump continuously draws hot, dry air across these water surfaces, the evaporation and the cooling is continuous. A 2021 microclimatic field study in the traditional Huizhou villages of Xidi and Zhifeng recorded dry bulb temperatures inside skywell basins running consistently 4.7 to 7.7 degrees Fahrenheit below ambient outdoor temperature. That differential was driven primarily by evaporative cooling, not shade, not wall mass, not airflow alone. Wealthier households extended this underground. Subterranean drainage channels routed rainwater beneath the courtyard floor, circulating it around the main living quarters before exiting the property, a radiant subfloor cooling network that lowered ground temperatures throughout the structure. The building materials reinforce the effect from every surface. Unglazed blue brick, porous lime mortar, and timber framing are all hygroscopic. They absorb excess moisture during humid periods and release it during dry heat, stabilizing interior humidity without mechanical assistance. Nature provides the ultimate refrigerant. These builders knew how to build the radiator to harness it. The air is cool, the walls are holding, but the sun is still hitting the roof. Without addressing that, the top of the building becomes a furnace radiating heat downward into every room below. That required the fourth component, the one that looks like decoration but functions like a precision instrument. The curved, flared roof eaves of traditional Chinese architecture are called Siheyuan. Striking to look at, but they are a passive solar switch. The Siheyuan overhang is perfectly calculated to intercept the steep summer sun. At peak summer angles, which reach roughly 73 degrees in the north, the deep projecting eave casts a shadow directly over south-facing walls. Measured reductions in direct solar radiation load reach 54%. During winter, the sun drops to 27 degrees and passes beneath the eave, flooding rooms with direct light, striking the interior high-mass walls and warming them. This geometry is a universal principle in traditional Chinese architecture, adapted to local latitudes. The same thermal battery that buffers summer heat now stores winter warmth. One structure, 2 seasons, 0 mechanical components, and the system adapted over time. Historical analysis of more than 200 architectural remains across northern China shows builders systematically increased roof pitch from roughly 27% to over 30% during cold eras, including the Little Ice Age, to handle heavier snow loads without structural failure. These were engineering responses to changing environmental data. The buildings were adaptive. 4 components, 0 electricity. A building that cools itself, pumps its own air, regulates its own humidity, and adjusts to the season through geometry alone. So if this system worked, and the data confirms it did, why did we stop building it? This component does not involve physics, it involves economics. The abandonment of passive cooling was not an engineering decision. No study showed these courtyard systems had failed. No commission determined high-mass walls were inferior. The systems were not replaced because something better came along. During rapid urbanization across China in the mid to late 20th century, cities faced enormous pressure to house growing populations quickly and cheaply. The Siheyuan requires a horizontal footprint, courtyard space, setbacks, and a low-density layout that is difficult to scale for the needs of modern, hyper-dense urbanization. As cities exploded in size throughout the 20th century, the shift to high-density concrete blocks was driven by the urgent, massive demand for affordable housing, a scale that the sprawling, resource-intensive courtyard model could not satisfy. We traded the passive, site-specific efficiency of the traditional home for the rapid, standardized efficiency of the modern apartment block. Built faster, permitted faster, sold faster. In Beijing alone, more than 90% of the original 7,000 to 8,000 Hutong and Siheyuan neighborhoods were demolished or fundamentally altered between 1950 and 2000. Across the country, historic southern Skywell districts faced the same fate. The thermal batteries, the Skywells, the cold lanes, the evaporative cores, gone, replaced by thin-walled concrete boxes connected to a centralized electrical grid. The same logic drove American residential construction. Wood framing and drywall are fast and cheap to build. The long-term energy cost is not carried by the developer. It is transferred to the occupant as a utility bill, paid monthly, for the life of the building. The developer's incentive is to minimize construction cost. Your incentive is to minimize lifetime operating cost. Those two incentives point in opposite directions. And for 70 years, the developer's incentive has been winning. This is the efficiency trap. Modern construction is efficient for the builder, expensive for the occupant, and fragile for the grid. And that grid, as Phoenix demonstrated in 2023, is not built to absorb unlimited peak demand during extreme heat events. We did not evolve past these courtyard systems. We traded them for a faster construction schedule and a lifetime of monthly payments. We did not stop building them because they failed. We stopped because failure was more profitable to sell. Modern researchers have returned to these buildings with instruments, sensors, and computational models. The results are consistent. The 2021 CD and Zhifeng field study confirmed the evaporative cooling differential of 4.7 to 7.7 degrees Fahrenheit below ambient, without mechanical assistance. CFD simulations of cold lane air partition systems confirmed annual cooling load reductions exceeding 28,000 kilowatt-hours per structure. For context, the average American home consumes roughly 10,500 kilowatt-hours of electricity per year in total. Thermal lag data for high-mass walls, like those in the northern compounds, consistently produces an 8 to 10 hour delay. This is precisely the window needed to shift peak heat flux from the midday solar loading to the nighttime release phase. And modern architects are paying attention. Passive house designers in China, Europe, and Australia are reverse engineering these principles into contemporary construction. Vertical skywells in high-rise buildings, double-skin facades, thermally massive concrete cores. The vocabulary is new. The physics is 1,000 years old. The cutting edge is pointing backward. These courtyard systems are a benchmark. Every component, the thermal battery, the solar-powered air pump, the evaporative core, the seasonal solar switch, solved a specific engineering problem with no moving parts, no power source, and no maintenance contract. The builders who designed these homes understood something modern construction has forgotten. A building is not a shell, it is a system. And a system that relies on nothing outside itself is the only system that cannot be taken from you. If that kind of knowledge matters to you, click subscribe. The next story is one click away.